Good morning, everybody. Thank you for attending this very exciting seminar. It is not truly a webinar because the speaker is kind enough to be here. So he is in room 2680. And so a lot of people are here interacting with him before and after the meeting. So today we are excited to have the speaker, Dr. Jaim Nulman. He is the CTO and the Executive Vice President of Nano, a very high-tech additive manufacturing 3D printing company. So 3D printing company comes from, very advanced technologies to almost household technologies. So this one is a very advanced 3D printing technology for electronic systems. And he will be talking about how to utilize this very exciting 3D printing for communication and diagnostic systems. And the speaker is very well renowned in both the semiconductor and additive manufacturing industry. And he got his PhD from Cornell University on semiconductors. And then for the last almost 15 years, he has held a lot of executive positions in major companies. And one of them being the Vice President of Applied Materials, the largest semiconductor tool company that makes tools that change the world. That's their slogan. So he was very successful there, taking products to almost $1 billion market. So he knows everything from technologies at lab scale to $1 billion commercialization, which is what he's now doing with additive manufacturing in nano dimension. So he will talk about the opportunities and technologies. And we are very fortunate that they are right here in Miami. And also we are very closely engaged with them in the IUCRC Center. They are a sponsoring member. They also have contracts, and we also are excited that they want to have more coupling with senior design teams. So undergrad students who are in senior design, they please form your teams and let me know or let Jaim know so he can talk about the opportunities that 3D printing can enable for biomedical devices. Similarly, master students and others who are wanting to do internship. So with this rather long introduction, I would turn in the stage to Jaim and have him give his exciting presentation. Thank you.
Okay, thank you, Raj, for the nice introduction. It's a pleasure to be here. I already done my wave here after being interacting with Raj for over a year, I believe, already. And I'm going to describe basically what we call additive manufacturing for electronics and specify like that more than the traditional additive manufacturing, as you will see during the presentation. Just a second here. And we'll discuss what it is, what are the industry drivers, which in part we actually got some inputs from Professor Raj. Look at the biomedical applications in addition to all the DC to RF traditional applications. And most of these are examples that several of our customers are doing either in the industry or other universities. And we're open to discuss opportunities or things that you guys want to do. Share some of the work that we're doing currently with FIU. There are some results already from a print that was done a couple of weeks ago. And there is another print scheduled for next week next week. And we're really excited about the opportunity to work closely with the university. We are only half an hour north from here in Sunrise. And people who may be interested, we can coordinate a visit to look at the system and so on. I'm not going to describe the system in detail today. We consider that more of a commercial type of activity as opposed to an education activity. And then we'll summarize. So what is the additive manufacturing for electronics? If you look at the electronics industry, we have it all together, the electronic circuits, and we can divide it in two segments, basically. The integrated circuits, ICs, the semiconductor, and then the PCB printed circuit boards.
I can't see your face. Maybe your camera is blocked.
Okay, then basically right there in the middle, we are positioning the additive manufactured electronic circuits. which will be basically providing a bridge between these two technologies. As you will realize during the presentation, that's the capability. I just can figure out, for example, if we look at the biomedical sensing of liquids, let's say blood sensing or other things, and you want to identify with this, we can fully integrate that with the electronic circuitry. So the additive manufacturing electronics is usually divided in two sections. One is the most traditional one, surface conductive deposition, which is a single conductive metal layer, typically a silver paste or a silver nanoparticles ink, and is commonly defined as printed electronics. But what we bring to the table, and where it's this advanced technology, is they're able to do multi-layer dielectric and conductive deposition. Both materials are deposited simultaneously in the system. And that allows you to create a traditional circuitry as shown by this X-ray. This is a 6-layer electronic circuit, originally from a PCB design. You can see the vias there and the multiple layers of traces. But we can also create an example like this device. It's actually for a medical application. This is about 8 millimeters in diameter, 3 millimeters height, and has printed capacitive coupling sensors. Then altogether printed, you have also the coil for the RF communications, the Wi-Fi communications, as well as a socket for the battery. Okay. And then after this is manufactured, then of course we go into the assembly of the electronic components in here, as well as the battery. And the X-ray on top shows you basically the coil, which is right there, and the battery. We put it as a test to test the connectivity there. But basically what we do is, as I mentioned, is we deposit both materials simultaneously in the system. One is the dielectric, shown by this orange line, and then the silver nanoparticles. So just to understand how AME technology works compared to traditional PCB, the PCB traditionally is an analog process, is a lamination, pattern, etch, pressing, electroplating. Sometimes you can buy a starting board and only need to do some drilling and printing on the top, but the most common thing in the industry is the multi-layer. In the AME technology, basically, we build everything from the ground up, from zero. There is no other electronics, nothing in place. Okay. Of course, we could print also on existing circuitry as well, but this is the most common application, and that's what we're talking today. You can decide to fill as part of the process the vias. You don't need electroplating for what is called the plated through hole, because that's coated directly during the process of building these structures. And basically, it's a digital process, no lamination, no patterning. Some people are doing electroplating, especially when they want to have some, because this is silver, so the biocompatibility require gold or nickel gold type of coatings there. But because it's digital, a very important thing is that you can create the vias and the connections in any shape. They don't need to be limited to 90 degrees. Or you can eliminate the vias altogether. We see some direction of how the industry is asking us to go on that, because by doing that, you reduce the distance between the ICs, and therefore you can increase the speed and the packing density. So the concept here is that if we look at the traditional, which is in the middle of the PCB manufacturing, which has many steps and processing tools, we basically enable everything to be done in one single system. Sometime in the future, we'll see the system also having a pick and place integrated in there. That's not available today, but that's the direction that they eventually will end up going. And then the only thing to be done is the testing at the end. So this will be not only the simplifying the cycle time and the cost, but also making this process green, because there is a lot of chemical consumption and waste in the traditional PCB industry. We already went through this. I know it's duplicated, sorry. So basically, we're going from a digital design file to a printed AME. And for that, you have a Gerber, ODB++, or STL file, depends on the source of the design. Because it could be not only from an ECAD, it could also be from a mechanical CAD. Then the system converts those into a pixel in a digital file, and then sends the signal to the printer heads to start the deposition. You get that the layer deposited, then you cure it, dry or sinter, depends on the material. And you start building that structure pass by pass, layer by layer. And then when you add the second ink, then you start building it in parallel, both materials, wherever it's required. So let's look at applications so that I'll give you an example of what can be done. I don't intend to go into dive too deep into them, but at least to give you a sense of what can be done. And this is basically something that borrowed from Professor Rash, where basically the trend in the electronics industry is to go from the traditional surface mount technology of components into a full embedded and packaged type of device, either a full structure or chiplets. And we'll see some examples of that in the presentation as well. The benefits of that is basically thinner films, thinner electronic components, as well as a higher packing density and therefore higher speed of the devices as well. So examples that also working with Professor Rash, we can see here, it could be RF and millimeter wave packing for reconfigurable RF packages, 3D antenna in packages, power electronics, wireless neural recording, antenna mixer or diode with matching networks and things like that. And actually that's some of the work already that we are working with FIU, as well as other wireless photonic sensors, which are also in the plan to start working on. But this is an example here where we see a work that our customer in Germany, Hensoldt, has done, and they have released that, even though it's a military organization. What you see in the video on the right is a motor that the stator was printed, the coils, and then not printed on this system, but creating it, taking a small plastic disc and mounted some magnets there, created the motor to do it. Actually, today they already have a drone built completely in this way. In the middle, you see the capability, because it's additive manufacturing. You can create any shape of the design that you need to. You're not limited by drilling or laser cutting. You just directly print what you need. And then you can do also traditional electronics as shown on the left-hand side. Another example is another customer also in Europe, in Rehau in Germany. They are basically making commercial products. And we designed with them a completely 3D with embedded components. This is a sensor to adjust the lights in the room. You can select by touching these 4 pads at the bottom here, as we saw, the color of the LED, and then by touching the LEDs themselves, basically you select the intensity of the light. As doing this, one thing that we have done is basically create passive components such as capacitors as part of the manufacturing process of the electronic circuitry. And this is an example of a cross-section of a capacitor that has 55 layers. The video that you see there basically is a board that we designed to test and prove the functionality, where we have 4 capacitors and then electronic circuitry that changes the capacitor into a fixed resistor and then changes the frequency by changing the RC constants of the LED on your left-hand side there. Like that, also going into the RF, we have created low-pass filters, and this is a cross-section of a low-pass filter shown by the X-ray. In these particular cases, there are something like 1 to 2 picofarad capacitors and transmission lines in between. And now we look at the characteristics of this so we can get an idea of how this thing is different from the SMT technology. This is the performance of these capacitors, particular design here on the thickness of 35 micron dielectric, between a couple of picofarads to about 3 nanofarads. The variation is very good. It's actually below what the typical variation in the industry is. It's less than 1.5% from capacitor to capacitor. Leakage current, actually, we couldn't measure it in reality. We just put a number here because just couldn't measure it, but it has also very high breakdown voltage, and the temperature stability factor is about an order of magnitude compared to ceramic SMT capacitors, which are considered the high-end materials for capacitors in the industry. And that's reflected as when we look at the change in Q factor as function of frequency. And we can see here that the AME capacitors, basically as shown by the black line here, have essentially no change in the quality factor of these capacitors compared to the SMT mounted ones. But very important is when we look into RF applications, if we look at the impedance as function of frequency, we can see that the impedance for the commercial capacitors increases, and they were mounted on the same type of structure. Okay, so basically everything is the same except that one is using SMT, the other one is using the printed capacitors. We can see the increase in the impedance here, and compared to the AME capacitors, that change as function of frequency is at least a factor of 3 less. And why is that? For that, basically, we created an equivalent circuit and did a simulation to see how the performance of these things will match. And the answer is very simple. It's basically by not doing the encapsulation that is traditionally done with SMTs and the solder reflow, we eliminate the parasitics which are involved on that. And you can see that here, basically, when you look at the resistance, for example, is basically more than order of magnitude lower. Same thing for the inductance. So basically, the AME capacitor behaves like an ideal capacitor. Like that, we also build, as I mentioned, the low-pass filter. This particular one is designed for a 5 gigahertz cutoff. Typically, if we make this thing with we take a off-the-shelf and mount these low-pass filters, they will stop cutting off the frequency about between 4 to 6 to 7 gigahertz at higher frequency. But because we eliminate in this case the encapsulation as well as the parasitics, the cutoff signal remains below 25 dB all the way to, in this case, to 20 gigahertz. That was the maximum frequency we tested this at. But because it's 3D additive manufacturing, you can also design that with an integrated shield, okay? And this thing basically ends up with an order of magnitude lower weight compared to commercial package low-pass filters. And this is the simulation that we did for this particular case. And then, of course, we can see here the test results. And because of the resonance with the package, with the encapsulation, and then it stops cutting off the frequency around 15 gigahertz. Okay, but this just gives you an example of things that can be done. Having said this, let's look at other work that has been done in this case with the University of Technology in Sydney, Australia, where they focus on RF applications, millimeter wave applications. And here, basically, they were able to build patch antennas on a different array and multi-layers, as opposed to a single layer of patch antennas. In this particular design, has three stacked antenna layers, 1 ground plane and 1 feed network. And the feed network is under the ground plane. Okay, and then in the ground plane, there is a via where they feed the signal into the matrix. And this case is designed for a linear polarization, but with minor changes in the design, basically it goes into a circular polarization, as you can see here in the shape of the antenna itself. So you can create in the same structures, basically, a combination of both and control them electronically. A benefit of going from a single patch antenna to multiple ones or the matrix altogether, we can see it here where from a single patch antenna, a dB operational bandwidth of around 6% going to about 83% when you basically increase the number of patches and layers. Like that, basically, they also build a bandpass filter, and this is fully integrated here. Look at the dimensions. They're about 3 millimeters by 1.5 by 6.6 millimeters thick. And the flexibility on the additive manufacturing is you can then create the placement of the ground plane anywhere in the structure, so you can optimize the performance of the bandpass filter there, and also basically design the value of the capacitors and the quarter lambda resonators accordingly, and optimize that and make it part of the entire circuitry altogether. You can see here on the graph, basically the fabricated bandpass filter compared to the simulations. We can actually get to very close values by basically updating the simulation with the proper dielectric constant. Another example of what the team over there has done is the creation of this metamaterial lens antenna, like a Fresnel lens. As you guys may know, as you go to the terahertz spectrum, basically, if you have weather conditions, trees, and other things, they will diffuse the signal quite a lot. What this ambient is able to do is to focus the signal, improve the gain at the fixed at the desired frequency. However, what was done here, and is you can see this is about 6 millimeters in diameter. Actually, we have a dual bandpass, a dual Fresnel lens here. It's operating at 2 frequencies, with having 2 lenses basically manufactured one on top of each other directly. And here, for example, you see at 75 gigahertz, the gain at the center frequency, which goes from about improved by a factor of almost, I think it was from a 6 dBs all the way to around 21, 25 dBs. And then similarly, work also done for 120 gigahertz, which is the other frequency in this design. We can just take this graph here and replace it by the 120 scale, and then it's the same graph. Okay, so this is given examples on this how it can be done, but then furthermore created a phase array type of antenna, and this is the unit itself. As you can see here, multi-layers of the metal to create a dual beam transition, and then distribute that on the board, on the printing according to the optimized design and simulations. And here basically you have the data for the dual beams, the left-hand side and the right-hand side signals. Going to a different direction, some of our customers also looking how to use this technology to improve the performance of the traditional PCB technology. This is from a board which is commercial right now for controlling the engines on buses, electric buses. And basically was converted to this board by using the ME technology, a combination of the electronic design and the mechanical design. And what was done here is first reduce the weight of the board by basically where there is no electronics, just using this honeycomb type of structure. But for those of you who operate with high power devices, here basically to control these electric bus motors, they need to operate signals at 1,600 volts. And for that, basically, it's the fact that if you have lines where you have very close this voltage going across, you can have what is called creepage, or a leakage of electrons from one side to the other. And there is a standard on the industry that requires what's the minimum distance for that. What was done here basically is create these walls around these 3 areas of high voltage, and use basically the lateral and vertical dimensions to comply with the standard on the distance, and therefore be able to reduce the size of the board in this section. Other components here, in this case, is more in the manufacturing side. This customer had some rejects sometime during the assembly process, because when they put the screws here to mount it to the body, sometimes the screwdriver slipped and damaged the electronics. So they created this walls around the areas where the screws go, so that if it doesn't, in case of the screwdriver slips, it doesn't damage the electronics. So just give you a flavor of things that the industry is starting to look and what to do with this technology. Now, going into back into the RF area, and there is a circuitry called T-bias, which is especially in the automotive industry, to put a different DC bias at signals that are coming from the different cameras, especially for the automated self-driving cars. And traditionally, basically, in the commercial area, they use the ECAD to create these coils. Okay, and these coils, as you can see here, this is an optical picture. You have basically, in this case, is a half circle, a via connected to a half circle, and done. So you start building this thing in layers, but connecting half circles with vias. On the left-hand side, you have actually a coil that was designed in a mechanical CAD, and it's a continuous coil. So as you can see here, the inductance is better. Also, the DC resistance is lower, and the normalized factor is better, the quality factor. as well as the impact is much better compared to the traditional ECAD because you don't have the vias and the parasitics that are involved with that. Usually controlling the via resistance in traditional PCB manufacturing is difficult. Now, let's look at the biomedical applications. And basically what we see from the different customers looking at things that will do sensing in the body, from physical sensors to optical sensors, or combination of them, chemical sensors as well, thermal sensors and electrical sensors. And we'll see some examples of these. And the direction is to eventually go into some body control based on that, especially for people that need that help. And also eventually going to that data management. So an example basically that's been looked by the IIT in Italy, the Italian Institute of Technology, is to look at the smart patches or electronic tattoos that show you exactly what they mean by that, or some antennas with sensors to look at the skin properties. So here is basically the underlying antenna to enable a wireless sensing of conditions on the skin. And what you see on the graph that you see on the right-hand side is basically an optimization of the thicknesses of the layers here for both the conductive as well as the dielectric in order to obtain the right signal to do this work. And this is a published paper, so it can be looked into there. Another work done by the same group, a different subgroup on there, is basically a sensor to look at the cardiovascular pressure. And this is what they call it tattooable. Basically, it's a very thin layer of dielectric with the sensor and the electronics in there, which gets attached to the body. And then you can see there the signals that they measure and do that. So this is some examples of the direction that is going there, just to give you a flavor of what other people are doing. And I'm sure you guys are doing even more than that here, that we'll see if there is something more to do except what we have started already. With FIU, basically, we're working with closely with Professor Wallace, of course, and then Professor Rash, as well as Wei Qianling and Satish in the RF. Today we have Melanie, who's here, and also here working with the projects, and there are some printing already that has happened and results. Example of this is shown here with the wireless neurosensing. Melanie is optimizing the receiver here with the dual antennas. She already got some results. If I remember correct from earlier review this week, it's about 4 dBs improvement in performance. And but the key thing is that she was able to create different versions and see the tolerance of the process and variation to pick the right design and the right process for the performance required. Believe next week with here we're going to print the design on the bottom, where basically we are going to actually create this bipolar. We embed this bipolar transistor inside the board itself and have direct wiring printed into the transistor itself, and then we'll characterize that, and eventually this basically provide the overall signal that is required for sensing these the brain signals and transmitting them to the analytical equipment. Another work that we're working with Professor Lin and Professor Rash is basically creating a product that will be attractive to the industry, where we have basically biophotonic sensors that will be manufactured here on a flex material, but then it will have a motherboard where this thing will connect to, where you have embedded electronics from power management to the signal processing, as well as the RF communications. And lastly, but not least, with Professor Satish, basically today the industry is very common to RF designs using ceramic components, where you print the metals there and you basically connect them in a cube shape, a matrix like that. And then you basically mount that on top of the signal feed and eventually the electronics there. So, but this is bulky in general, and what we are doing there basically now is designing this into the AME structure much smaller, and basically making everything integrated. So you also eliminate the contacts, like would be equivalent to SMT, and create basically reduce the losses and improve the performance of these devices altogether. So with this, I just want to say that the AME devices and circuits is your imagination is the limit. Okay, it's a digital process. You can create anything that you want to. The only thing that the only limitation here will be basically your the capabilities of the design tool or the fabrication tool. Some examples. Basically, some of our customers are asking us to go this direction. No vias, direct wires from a IC to IC, and sometimes even twisted vias. And basically, here's an example of a triple twisted. This is done for some noise isolation. But this is one example of, I cannot show the rest because it's a defense contractor, but they allow us to basically share this as an example of what the capabilities are. But as we said at the beginning, the direction is to go to further integration, making things smaller and thinner. But also some customers are asking us to go this way. Make it smaller, but also thick, higher, so that basically, especially for very small spaces and microsatellites, this is more or less the direction they would like us to go. And we have done some proof of concept, in this case with our customer in Germany, where we took an original PLL board, as you can see here on the left-hand side, and divided into 3 sections, embedded the components, and then basically created this structure, which is about 9 millimeters in thickness and about 2 centimeters in X and Y. If we look at these structures, and you can see here the design concept, there are no vias at all here, and everything looks here more like a chemical factory or refinery as opposed to an electronic circuit. But if we look at the X-rays of this thing, you can see here the first layer. This is a complete device from the top. And here you can see a side view, focus on it, where actually they have here even some micro coax cables. These are about 500 microns in diameter for the shielded section, and about 100 microns on the trace itself in the middle. And just to give you an idea, this is a CT scan of the real system in there. So with that, I would like to thank you and open for questions. And as I said, the limit here is your imagination. Thank you. Yeah.
So I have 2 related questions. One is, what is the pixel resolution, or in this case, voxel resolution that you have? And the second question that may be related to this is how far we are going to the 3D printing of semiconductors.
Good question. Today, basically, the process we have released is a 75 micron trace. We do a rendering at 18 microns. That creates limitations, basically. The rendering, future generations will go down to 50 microns. With respect to semiconductor printing, there is a startup in spin-off from a university in the Northeast, which is doing additive manufacturing semiconductors. But I would say that the capability of that may be good for some MEMS, but not for advanced ICs.
Any idea how to, one area of interest in biomedical application is microelectrode surveys, and in particular to create. So there is this new technology that you created microelectrode, and the folding component, which is in this case, I mean, normally use silicon. They use a biomaterial that is digested by the tissue. So you set that solid microelectrode, and after a few hours or days, the solid component of this dissolved because it's digested by esterases, things like that, and then remain the very thin conductor there that reduce inflammation and response from the reactivity from the tissue. Do you have any material that could be used in this printed that dissolve with biological tissue?
No, this is actually, we use the only two materials, the dielectric and the silver nanoparticles conductive. This will require embedding maybe that material in that channel, as long as it's horizontal. Or you can make it, the other thing is to see how to, if the material is just thinking aloud, okay? If the material is it's a paste or something, then you can dispense it in points. Okay, so you create a matrix of points, and then at the bottom you have the sensing for it.
Promising. Just thinking aloud.
Of course. Of course. Any other questions?
Yes, very good presentation. Thank you very much.
You're welcome.
I was wondering if you have any capabilities or plans to print resistive material.
In future systems, yes. That's it's not a big issue. It's just the carbon-based, typical carbon-based, carbon nanotube-based inks. This printing system has only 2 printer heads capability.
I see. And so because we're looking into maybe printing some resistive material buried underneath a multi-layer structure, but an alternative would be to use buried resistors, tiny ones. So how does it work if we want to bury components?
It's basically very simple. As you are printing, you want to have it completely encapsulated, for example. You start to print, you define the CAD system where you want the cavity to place it. We can then select if you want to print the traces first and then use a silver epoxy or something to build your device, or the other way around. You put what's called chip first. You put your resistor in this case first, and then you print connecting the traces connected to the contact points there. And then you can continue to.
Okay, that's interesting. So another question. So would it be possible, for example, to put heterogeneous substrate in the way that you would start the printing, and then we would come with a substrate from outside, integrated, and then you continue printing on top?
Yeah, that's possible.
That's possible.
We just need to make sure that the materials are compatible from the point of view of the coefficient of expansion.
Okay. Okay. So I have one last
Sure.
about the characterization of the dielectric constant of that you use. It varies a lot. I mean, at the higher frequency. So, and I couldn't. Did you characterize it after 20 gigahertz? Because I couldn't see it.
Yeah, we have no characterization. We upgraded our system not too long ago.
Okay.
I can look into that data and make it a lot.
All right, that's great. Thank you so much.
About for the metal, like for millimeter wave, as we know, the spin depth is very low. So in that case, we worry about the surface roughness of the conductor or traces. So what kind of surface roughness we have in the material printed in there?
You are 100% right, but let's keep in mind that as you shrink the sizes, you got, for example, all these devices, if you make them very small, will be very close to almost impossible to see the losses. You'll see them when you make a long straight line, right? And over there, you will see the effect. Having said that, yeah, those are factors that we are seeing how to improve altogether, especially for when we go commercial. Commercial applications. And basically the losses are a composite of not only the roughness, but also the conductivity of the metal. Okay? And those traditional people say, well, this high frequency digital wave is on surface conduction, but the bulk conductivity affects the losses as well. And our analysis have indicated that as long as you are above 50% or 60% from bulk, the gain or the improvement is almost insignificant. So we're working continuously on on improving those things. We're also working on developing new materials, especially in the electric side. Our target and the analysis have indicated that go to a 10 to minus 3 level of the tangential losses is what the industry needs.
Thank you.
We're not there yet, but there is a paper that's been sent to publication right now, also with the UTS guys, that shows basically that the small devices don't have that loss present because you cannot see the person.
Hello, I have a question. Thank you for the presentation, by the way.
welcome.
I was wondering, so are you currently able to print conductive materials onto, let's say, ceramics at the time? I know you talked about that in the antenna slide. I was curious about that.
Well, the work that in the antenna slide we didn't do that. Okay, that's the traditional process. We can print if the ceramic is a material you consider embedding. Yes, I mean we can print them. It's not, but as long as also the size. We need to look at the size because we have a vacuum that holds the material down during the print process. Because printing is a process that starts or operates at 160, 170 degrees Celsius. So if you want to have good control and quality of the inks, the curing of the ink, you need to have a good thermal control there. And it's different, for example, as compared to the printed electronics, the traditional single trace, which is either done in screen printing or an aerosol printing or the single trace.
Okay, and that sort of leads into my second question, which is the post-processing is as far as the manufacturing of the PCB boards with the simultaneous formation of the dielectric and conductive layers. Is there post-processing required for that?
No, the only post-processing is basically the assembly of the surface mount components and solder from.
Okay, great. Thank you so much.
You're welcome. Basically, just to because probably the background comes. Basically, we cure the dielectric as soon as we deposit it with the UV lamp, and we dry out the solvents of the conductive ink as well as sinter it also as soon as we deposit it.
Thank you.
Any other questions?
And I would be glad to arrange a visit and you guys can see that.
I would very much appreciate that. Yes.
You're welcome.
Yeah, actually, I have a very similar question. So how they print the silver on glass slide?
Yeah, we can print in glass lines. But again, it's the same issue, temperature control.
Okay.
So basically, when we print in glass, we use sometimes for calibration of the system. We have a glass sheet which is of the same size of the substrate, which is about 200 millimeters by 200 millimeters.
Hello, good morning. I have a question.
Sure.
So for a student who wants to get good at this, let's say, what would you recommend would be the things that they need to learn besides software packages and of course circuitry?
So if they understand the ECAD software packages, then you just export the output files, either ODB++ or Gepper, and that's all what we need. Okay. But also we have introduced, I just didn't share that today, an ability to export today from Altium into SolidWorks in electronic design and integrated with a 3D structure directly there. And I think you can also, you don't need to hear directly from me. You can ask Melanie and already who did this work and see how difficult or complex it was to do, or easy it was to be done.
All right, thank you. Appreciate it.
Welcome.
Let me also introduce Manuel. He works on 3D printing of tissues and cells for regenerative medicine. But they print in their lab, but I think again they use more traditional biomolecule printing.
So hydrogels,
Yeah, okay.
the substrate.
So that's a single dispenser, right? Yeah.
So any other questions?
Do you have a question?
Yes,
So how, I believe it's kind of a layer by layer process. So
correct.
how thin is a slice? How thin can a slice be?
It's less than nanometers.
Oh, okay. So huge control here. Okay.
I think one important direction is exactly what you said. We want to print and then incorporate other devices into it, but may not be easily achieved with
Good morning. I don't have a specific question. I just wanted to introduce myself. I'm Daniela Radu. I'm looking forward to hopefully collaborate in the very near future and perhaps training some students to your facility. I see Mark is in the audience. I just wanted to say hi. I was not able to attend in person today, but definitely I'm sure we'll have a chance to meet in the future.
We have plenty. I'm coming quite frequently here, and I'll let you know when next time, so we can maybe have some time.
Thank you so much.
I'm looking forward for the start of your work as well.
Absolutely. Will you and Mark will be the first to learn about that.
Okay,
Thank you.
sure. Thank you. Nice meeting you finally.
Thank you. I think for people who are not here on Zoom, he already got some samples. A traditional circuit board and a tidally printed circuit board, and to show the substantial miniaturization, weight reduction, and all. So we can just pass this around.
And when you can compare, basically, the big one is a traditional PCB type of design. The other one is an AME design, and the size is reduced by 30%. 2 weeks ago to show you guys the X-ray of that. So,
And I'm not sure if there are any undergrads, but they're also interested in mentoring senior design projects. Again, it has to be channeled properly so that there's a good synergy between the senior design goal and the company's strategic needs. So they're also interested in engaging with undergrad teams and also other grad students for spending time at their company. So if anyone is interested, you can speak up, or we can contact Jaim separately.
correct.
So I think we have a couple of students who are interested in follow-up meetings, so we can start that. But before that, let me close the seminar, unless there are any other questions for one last time. If not, again, thank you very much for all for attending. The seminar is co-sponsored by the IEEE Electronic Packaging Society and FIU, and also the EMBS. So Alejandro and Reshmi are here recording it, and they will also post it, hopefully. So it's co-sponsored by the IEEE, EMBS, and EPS societies, student chapters at FIU. And thank you very much.
Thank you.